Tracy, do you want to check and see? Live streaming should be going on YouTube. You're on mute, Tracy. Okay. Thanks. So just give it a few more minutes here before we get started. All right, students or Joe, can I get a thumbs up if you guys are ready to go? I don't know if that was a thumbs up, Josh, or if that was like a little bit later. There you go. Okay. All right, well, then I'll get started here. So hello, everyone. Thank you for tuning in to our high school student seminar. My name is Amanda Pfeiffer. I'm an education coordinator at the Canadian Light Source. Before we get to the students and their presentation, I just have a few housekeeping things to take care of. So we are live streaming right now through c.l.s. YouTube. So if you want to have your videos off, that is perfectly acceptable. Likewise, too, it's probably going to help with the students and their internet connection with their bandwidth. So feel free to turn off your video. For those of you joining in through WebEx, you do have the option to change your layout. So if you look in the top right-hand corner, there should be a layout icon. If you click that, then you're going to click side by side, so that when the students are sharing their slides, you can see both the slides and the students as they speak and present. There will be a question period at the end of the seminar. So if you have a question, feel free to post it in the chat or unmute yourselves and ask the students directly. Also note, they do have some guests in their classroom. There might be questions coming from them as well. So we'll just have to coordinate that a bit. And I think that's all I need. So I'm going to stop sharing my screen and let the students get started as I introduce them. So we have students connecting to us from Burnaby, British Columbia at their school, St. Thomas More Collegiate. They're a group of 11 students, and they used the IDEAS Beamline in early February to investigate the presence of heavy metals and the possible connection it has to pesticides in beeswax samples. We also then used the Brockhouse Beamline to investigate the different structure in these beeswax samples. And they're going to share with you their story and what they learned. So I'm going to pass it off to you guys.
What's this? Okay. Sorry. Thank you to all for coming to our presentation. Brockhouse, Beamlines, and Beeswax. Oh my. Our project investigated the effects of pesticides on the chemical composition and crystalline structure of honeybee beeswax. Now we'd like to give our First Nations land acknowledgements. As a part of STMC's Truth and Reconciliation journey, we acknowledge that we are on the ancestral and unceded homelands of the Hunkaminam and Squamish-speaking peoples, and the extended appreciation for the opportunity to operate the school on this territory. We also acknowledge that our samples were found on the traditional territory of the Tawasim and Musqueam First Nations, and all of the Hunkaminam-speaking peoples, as well as the unceded traditional and ancestral lands of the Kwantlen, Kusi, Semiahmoo, Kaikite, and Coquitlam peoples.
The C.l.s. in Saskatoon, Saskatchewan is located on Treaty 6, land in the traditional territories of the Nehiyawuk, Anishinaabe, Lakota, Dakota, and Nakota nations, and the homeland of the Métis. As students, we respect Indigenous ways of knowing and oral traditions. We dedicate ourselves to moving forward in the spirit of partnership, reconciliation, and collaboration.
Moving on, let us introduce the members of our team. My name is Carson, and I'm in grade 12.
My name is Adarsh, and I'm also in grade 12.
My name is Aisha. I'm also in grade 12.
My name is Brandon, and I'm in grade 10.
My name is Chase, and I'm in grade 12.
My name is also Chase, and I'm also in grade 12.
My name is Natalia. I too am in grade 12.
My name's Josh, and I'm in grade 12.
My name is Matt, and I'm a grade 12 student.
My name is Alicia, and I'm in grade 12. My name is Angelina, and I'm in grade 11.
Our members have diverse interests, and those going into post-secondary are pursuing various fields, including science, music, applied science, and business. We're all active participants within our community, competing on athletic teams, performing in band, and serving on student council. Our teacher and advisor is Mr. Muse, a senior physics teacher at St. Thomas More.
St. Thomas More is a Catholic co-ed high school in Burnaby, British Columbia, led by the Global Congregation of Christian Brothers. We house a total of 695 students and approximately 75 staff members. Our education is based and focused on the 7 essential elements of Blessed Edmund Rice. We can actually relate this project to the 7th essential element, which is to pursue excellence in all endeavors, which means to develop an educational culture that fosters the growth of the whole person, higher order thinking, and lifelong learning. Since we are promoting a strong academic curriculum and striving to achieve excellence in this research project, shows that the 7th essential element is instilled and displayed in our education. Over on the right of the slide is our school beehive. This beehive is maintained by 2 of our teachers at school. Unfortunately, though, this beehive is now dead due to a destructive bee-brood disease called American foulbrood. This has then inspired us to research the reason behind the sudden disappearance of bees.
This infographic is representative of the impact bees have in Britain, where they contribute 400 million pounds to the economy and are pollinators of 70 types of crops. Similarly, in Canada, bees are one of the most important pollinators in our ecosystems, and they, along with other insect pollinators, are directly and indirectly responsible for 1/3 of the human diet. They are vital to our environment, food production, and honey production. The commercial value of bees to crop pollination in Canada is estimated at over $2 billion annually, stated by the Senate Committee on Agriculture and Forestry. Bees are essential to our environment, and without them, much of the food that we consume daily would not exist and multiple crops would disappear. Unfortunately, the use of pesticides, in addition to environmental factors, have been detrimental to the bee population. The honeybee population in the United States decreased from 3 million to 900,000 just in the span of 4 years. Due to the importance of honeybees, we were also inspired to focus our research towards them.
Beeswax is one of the 2 major components of honeycombs, the other being propolis. It is secreted by worker bees that 8 wax-producing glands on their abdomens. This wax is secreted as a liquid, but once it is exposed to air, it begins to harden, turning colorless and brittle. Bees then chew on this wax, allowing it to soften and be shaped into a hexagonal cell used in the honeycomb composition. When the bees chew on the wax picks up different substances such as honey, pollen, and propolis, explaining the darkening color. Bees produce and use beeswax because it has many favorable characteristics, such as not being soluble in water to prevent moisture from ruining the honey, and because it is strong and easily shapeable into hexagons, which is an ideal shape because of them fitting together so well and being the most efficient for storage. Beeswax consists of more than 300 components, the main elements being carbon, hydrogen, and oxygen. The most important part of this page is the formula, which is on the screen. This formula is an important aspect of the Brockhouse data analysis, which will be brought up later on.
Crops and weeds around honeybee hives are often treated with pesticides to kill pests, such as the Varroa destructor mites and the Nosema apis fungi, both of which are shown at the top right. Beekeepers treat these plants to prevent pests from attacking the nearby hives, and thereby to prevent the occurrence of colony collapse disorder, which is a phenomenon that, like its name, marks the sudden death of entire bee colonies. Researchers have suspected multiple causes for CCD, including the unexpected disappearance of healthy worker bees, pathogenic invasion, and many more. Studies have shown that colony collapse disorder does not have one single cause, and this is still undoubtedly an area of debate that requires continuous research. The pesticides used on crops leave behind residue, such as the 3 chemical compounds listed here. Many of these compounds belong to the class of insecticides known as neonicotinoids, which seem to be strongly related to bee poisoning and are already banned by the European Union. Even at low field realistic doses, pesticides can have sublethal impairments on bee colonies, and extensive pesticide exposure has been linked to a greater rate of colony death. Both pests and pesticides have a negative impact on honeybees. As seen here in the diagram, everything works in a cycle. Even though herbicides keep crops free of weeds, they result in monoculture and therefore reduce food diversity for bee colonies. This, alongside with pesticide exposure, will decrease honeybee immunity, making them more susceptible to parasites and pathogens. As a result of such effects, more insecticides such as neonicotinoids may be used, which further increases the level of pesticide residues that bees come into contact with.
This graphic shows how pesticide residues ultimately show up in wax. When crops are treated with pesticides, the chemicals accumulate in the nectar and pollen of the flower. Bees then arrive to collect the nectar and pollen for the purposes of making honey and bee bread. When the bees take the contaminated nectar and pollen back to the hives, they are stored in the hive's honeycomb, causing the pesticides to leach into the wax. An article from the October 2018 issue of the journal Environmental Pollution screened 133 samples of live worker bees, pollen, and beeswax for 63 different pesticides and found that the wax contained the highest level of miticides, proving that pesticide-like substances can manifest in beeswax.
As mentioned, even low concentrations of pesticide exposure and residue can be very harmful for bee colonies. According to several recent studies on these pesticides' effects, here are some of the specific ways that honeybees are affected. They will experience a decrease in acquisition learning and long-term memory, especially for worker bees, a reduced responsiveness to sucrose, which is their main source of carbohydrates, disruptions to their reproductive system, including elevated mating frequencies for the queen bee, as well as reduced sperm viability in drones. Last and probably the most important of all, honeybees will experience a substantial increase in mortality following extensive exposure to pesticides. All of these negative impacts of pesticides, just like the pests themselves, will lead to bee poisoning and eventually colony collapse disorder. And as mentioned earlier, honeybees are so essential and relative to our daily lives, both financially and environmentally. So by focusing on the effects of pesticides on beeswax, we can come up with conclusions that will be informative to the beekeeping community and simulate further research on this topic to protect honeybees.
Our hypothesis is that the presence of pesticides will affect the chemical composition and alter the crystalline structure of beeswax. The first goal of our experiment was to look at the differences in presence and relative abundance of elements within our beeswax samples, as well as the differences between our individual samples. We mainly focused on pesticide-related effects because we believed that if pesticides were present in our samples, elements which comprised its chemical structure would also be present. However, we looked for differences based on crop type and location as well. We expected samples near the same crop and from the same geographical locations to have the same types and relative abundances of elements. The second goal of our experiment was to determine the effects of pesticides on the crystalline structure of our samples. Not only are pesticides detrimental to the health of the bees, but they are known carcinogens in humans. If pesticides are able to alter the genetic code within DNA, we wondered if they could also change the organization of atoms within beeswax.
We obtained samples from Dr. Leonard Foster, who is pictured here in the bottom left. Dr. Foster is part of the Department of Biochemistry and Molecular Biology at the University of British Columbia and has been researching bees for a long time. He is currently doing agrochemical testing for specific pesticides in beeswax. And while he was collecting samples for his own research, he was kind enough to also collect samples for us. We received 14 cuvettes with 2 beeswax samples each, classified based on the apiary, crop, and exposure to pesticides. We also took samples of beeswax from the hive that died at our school from American foul brood. As mentioned earlier, one reason why we wanted to research beeswax was because of the beehive at our school. Dr. Foster collected samples from around the Lower Mainland, specifically in Langley and Delta, which can be seen on the map. Beeswax from hives next to cranberry crops were classified as cranberry, and these are the red locations on the map. Beeswax from hives next to high-bush blueberry crops were classified as blueberry, and these are the blue locations on the map. Beeswax from hives next to crops that have been grown with pesticides were classified as exposed, and these are represented by the squares. Beeswax from hives next to crops grown without pesticides were classified as unexposed in our research, and these are the circles on the map. Our sample preparation at school was limited. We placed each sample in a Ziploc bag with a label before shipping, as seen in these images. As we were not able to travel to Saskatchewan, Amanda Pfeiffer, the education coordinator, and Dr. Graham King, our science mentor and the scientist in charge of the Brockhouse beamline we used, helped us virtually with the sample preparation. For ideas, the samples were placed in sample holders and attached with tape, as seen in the pictures on the left. For Brockhouse, the samples were attached to capillaries holders with tape, as seen on the right.
XRF is a non-destructive analytical technique that is used to find the elemental composition of a sample. It does this by taking a sample and having it be hit by a primary source of X-rays, and then measuring the secondary or fluorescence X-rays that are emitted. These secondary X-rays that are emitted are created by the primary photons knocking out electrons from the atoms of a sample. The atom then becomes excited, and to go back to normal, an electron from a higher energy level drops down. But in order to do this, it must lose some energy, which it loses in the form of emitting a photon. We can then measure the energy of that photon, and from that we can figure out what element the photon was emitted from. XRF has a large range of elements that it can detect, and it is mostly limited by the beamline's energy level. For instance, on IDEAS, we got accurate measurements from argon atomic number 18 to bromine atomic number 35.
Here on the slide, we have an example of an XRF graph of one of our exposed cranberry samples. The peaks within our data reveal the presence of certain elements and its relative abundance with this particular sample. The elements that you see labeled on the graph at each peak are the elements that are present in the sample.
This graph displays the XRF data from our cranberry samples. This includes samples that have been exposed to pesticides and samples that haven't been exposed to pesticides. The data has been waterfalled or stacked on top of each other to clearly show the features of each sample's data. The peaks within our data reveal the presence of certain elements within each sample. We've labeled the element that each peak corresponds to on our graph. In general, our cranberry samples contained a relatively high abundance of zinc. Certain samples displayed a high abundance of bromine as well. Trace amounts of calcium and manganese were also found.
This is the XRF graph of our exposed and unexposed high-bush blueberry samples. It is similar to our cranberry samples graph in that all of our blueberry samples tended to have high relative abundances of zinc, and certain samples also have higher relative abundances of bromine. The relative abundance of calcium present seems to be slightly higher in our blueberry samples compared to our cranberry ones. New elements in the blueberry samples such as titanium and arsenic showed up, but only trace amounts of those elements along with manganese were present.
These are the general trends that we found in our XRF data. When comparing our results from unexposed cranberry samples to unexposed high-bush blueberry samples, we found that the cranberry samples had higher relative abundances of zinc and bromine. However, when comparing exposed cranberry to exposed blueberry, their graphs looked almost identical. This suggests that crop type has no effect on the relative abundance of elements within beeswax. Next, when comparing unexposed cranberry samples to exposed cranberry samples, we found that the unexposed samples had higher relative abundances of zinc and bromine. But when comparing unexposed blueberry samples to exposed blueberry samples, once again, there was very little difference between their graphs. This suggests that exposure to pesticides also has no effect on the relative abundance of elements within wax. Finally, we found random variations in the relative abundance of elements when comparing samples from hives in the same geographical area. This either suggests that there is no correlation between geographical area and relative abundance of elements, or that even slight differences in location can have a significant impact on relative abundance.
XANES, which stands for X-ray absorption near edge structure, is another analytical technique that, like XRF, uses incoming photons to measure the fluorescence of a sample. But XANES focuses on one element as opposed to a range of elements. And the reason that you use XANES is to try to figure out the species or oxidization state of the element you are testing. You can figure out the species by matching your graph with another graph from a peer sample of the same species. So how does XANES work? XANES works by starting the incoming photon beam at an energy level where the beam lacks enough energy to knock out the electrons, so no fluorescence is emitted. We see this at the pre-edge of the graph, and then over time you increase the energy all the way to the post-edge where most, if not all of the photons are exciting the element of interest. For an example, this is a graph of a bromine XANES, which starts around 13,410 electron volts, which is the pre-edge, and it goes all the way to around 13,575 electron volts, which is the post-edge. So after we finished running our IDEAS XRF scans, we had some time left over, so we decided to utilize IDEAS XANES capabilities. Now at this point, our group had a difficult decision to make because we only had time to run one element with XANES. So we decided to run bromine because it showed some of the greatest variation between samples with XRF and because it is an ingredient in some pesticides. So the graph that you see on the left are 3 of the 7 XANES scans of bromine that we did, and you can see the pre-edge, edge, and post-edge. All of these bromine XANES graphs are taken from a variety of unexposed, exposed, blueberry, and cranberry samples. So we expected to see some difference, but they all show very similar characteristics in the pre-edge, edge, and post-edge. So we know that whichever species of bromine this is, it is constant across all of our samples. So afterwards, we looked through previous research articles that had performed bromine XANES scans, so we could have a standard to which we could compare our XANES graphs. We were only able to find a single paper with similar XANES graphs of bromine. And from what we could tell, the species of bromine was either 4-bromine phenylenylene or 3,5-dibromotiazone. As you can see on the graph on the right, the edge and post-edge of these compounds are similar to our data on the left. We do not believe that either of these compounds are naturally occurring, and while we could not find much information on 3,5-dibromotiazone, we did find that 4-bromine is acutely toxic, although 4-bromine phenylenylene is not a known constituent of any pesticides. Further research is warranted to understand why it is present in the wax and what effects it may have. Also, as a side note, this was actually the very first time IDEAS had ever done a XANES scan of bromine. So that was interesting and a learning experience for both us and Dr. David Murray, the IDEAS Beamline scientist.
In addition to the IDEAS Beamline, we were fortunate enough to also access the Brockhouse Beamline in efforts to carry out our research in further detail. The Brockhouse suite consists of 3 beamlines, the low and high energy wigglers and the undulator beamline, all of which receive X-rays from one of 2 insertion devices from the storage ring. The beamline we utilized was the high energy wiggler. The high energy wiggler beamline operates with essentially any energy within the beamline's range, being 20 to 94 kiloelectron volts. This range enables many different abilities, but the one we have utilized is pair distribution function, or PDF. Why, you may ask? Well, because we were looking to determine the crystalline structure of our samples, and because we predicted beeswax to be not highly crystalline, we needed to utilize PDF to be able to see these structural components.
The data from Brockhouse starts off as a diffraction pattern, an example of which you can see in the bottom left of this slide. A diffraction pattern is the pattern that the X-rays make on the detector after being diffracted off of something. In our case, that something was beeswax. The different colors on the diffraction pattern correspond to different intensities of X-rays that diffracted off of the samples, as measured by the detector. From here, we can graph the intensity of detected X-rays as a function of 2 times theta, where theta is the angle that the X-rays diffracted off of the sample. That new function, seen in the bottom right, can be thought of as the sum of the intensities of X-rays that diffracted off of pairs of atoms within our sample. Using a mathematical tool called the Fourier transform, we can work backwards from this graph to find the distances between these pairs of atoms, which we can then graph. That new graph is known as the pair distribution function, or PDF. Next slide. Here's a screenshot of the program we use for analyzing our data, GSAS2. This screen is for controlling the parameters of a pair distribution function. Many of the parameters here are involved in maximizing the resolution and reducing the noise in our data. One such parameter is known as Qmax. Slide. Like I mentioned, the pair distribution function can be thought of as the graph of the number of pairs of atoms separated by a distance of r. Another way of looking at this is that this function is a graph of the probability of finding an atom at a distance of r from any typical atom within a sample. For example, if there was a large peak at 4 angstroms, that would indicate a high probability of finding an atom 4 angstroms from another atom. An angstrom, by the way, is just a unit of distance, specifically 1/10,000,000th of a meter. PDFs are useful for analyzing the crystalline structure of a sample, as it gives us information about the distribution of atoms relative to each other. If our hypothesis that exposure to pesticides affects the crystalline structure of beeswax is correct, we would expect to see a difference in the PDFs from our samples that were exposed to pesticides and those that weren't. As another note, you'll notice the relatively flat portion of the graph from around 80 angstroms onward. The flatness of this portion of the graph doesn't mean that there are no atoms that are 80 or more angstroms apart from each other, but rather indicates that there is little correlation between the positions of atoms at this distance apart or greater. That is, atoms are apparently irregularly positioned at 80 or more angstroms apart from each other. Another reason for the flatness of this part of the graph is instrumental drop-off. Slide. Awesome, thanks. This is all of our sample PDFs, as well as the PDF of the nickel we used to calibrate the detector overlaid on top of each other. The large blue graph is the nickel PDF, and the much smaller graphs with different colors are from our samples. You'll notice that the x-axis is R, measured in angstroms, and the y-axis is G of R, which is just another name for the pair distribution function. Nickel is a highly crystalline material, i.e. the nickel atoms are spaced very regularly, and this is seen by the sharp and tall peaks of its graph. However, nickel's graph becomes more shallow farther to the right due to the instrumental drop-off I mentioned in the previous slide. As you can see by the regular peaks of our beeswax samples, they do have some regular structure to them, up to about 60 angstroms. The beeswax peaks after around 5 angstroms are much shorter and much wider than nickel's though. This means that the atoms in our beeswax samples are positioned more randomly relative to each other than in nickel. Even so, there is some regular structure in all of our beeswax samples, and this surprised us.
The chemical bonds in our beeswax samples are very similar, which suggests that all the beeswax samples have a similar chemical makeup. Here we zoomed in to the PDF of our samples and focused on the peaks from 0 to 3 angstroms, as the bond length of several chemical bonds are in this range. We were able to compare the R value for the peaks to known bond lengths to identify bonds that appear in the sample. The first 2 peaks in the PDF are noise from the Fourier transform on the data. The next 2 peaks represent bonds. There is a carbon-hydrogen bond at 1.1 angstroms and a carbon-carbon single bond at 1.5 angstroms. 10 of the 12 samples, which are included in this graph, appear to have the same bonds. Also, the fact that we have bonding between carbon and hydrogen makes sense, as these 2 elements are prominent in beeswax, along with oxygen. The remaining peaks in this graph are for second nearest neighbors and represent the bonds between an atom and the second nearest atom to it. While there is a slight difference in the relative heights of the peaks in our graph, there does not appear to be a trend. With our limited sample size, we were not able to determine anything from the differences in the heights of the peaks of our samples. This is an area for future research. From this grouping of samples, we were, however, able to conclude that there was no difference in the bonding between exposed and unexposed beeswax. The pesticides do not alter the bonds. There is also no difference in the bonding of the beeswax between cranberry or blueberry crops, between different locations, or even between different species of bees, as our school hive was a different species of bees than our other samples, and is included in this graph.
There are 2 groups graphing the Brockhouse data, Alicia and Angelina as one group and Chase and myself as another. Because each group had slightly different calibrations on GSAS2, we decided to both graph all the data so that we could compare it. It is important to note that on top of having different calibrations, each group had a different Qmax, which is a parameter in GSAS2. A higher Qmax would result in more noise but more distinct peaks, while a lower Qmax would be the opposite, with less noise but more combined peaks. On the left, you can see Alicia and Angelina's graph, which has a Qmax of 18, while on the right, you can see that our graph had a Qmax of 15. Here we have a parallel analysis of samples A, which is exposed cranberry, and D, which is unexposed cranberry. We chose to compare these samples because they are exposed and unexposed samples of the same crop. As a result of the different Qmaxes, we can't tell if the differences in the graph are due to noise or an actual difference in the samples. Because the other exposed and unexposed samples are the same, there may be no difference. Here we are comparing the rooftop hive samples from our school. We chose to compare these because, again, they're the same species. The difference in the Qmax is very obvious here, as you can see that our low Qmax results in a graph that lined up, but is also missing the Fourier noise peak at the start, possibly suggesting we removed too much noise. However, something interesting about the samples is that the dark STM sample, the orange line, is the diseased hive that died. Dark spots on the beeswax were parts that were colonized by the American foul brood bacteria. The similarities in the graph could be partially illusory and potentially be accounted for by the low Qmax, as the lack of the Fourier noise peak might point to that. However, it could also be that the bacteria does not appear to have drastically altered the molecules in the sample. This is definitely an area that requires further investigation.
There is a regular repeating pattern that can be seen in all samples in the mid-long range of the PDF. The period of this pattern is approximately, as you can see in the graph, this pattern starts at 5 angstroms and goes up to 80 to show the presence of this repeating pattern before the crystalline structure drops off. The pattern is not seen in the nickel calibrant and indicates a chemical regularity in the not-so-crystalline structure of beeswax. As we are the first to analyze beeswax using a pair distribution function, this discovery is something we will definitely be looking more into. It is very interesting and surprising that there are such regularities in our samples, with 11 out of 12 samples somewhat stacked on top of each other, a pretty good representation. Notice that sample D is slightly different. This could be due to a difference in the composition of beeswax in that specific sample. What is especially interesting is that this difference is seen even when the noise and resolution are reduced in the PDF. Yet the bonds of sample D, shown in previous slides, line up with the majority of our samples. This suggests a real difference, and once again, we are going to investigate this difference further. Overall, this pattern proves that there are minimal relationship between the crystalline structure of beeswax and whether or not they have been exposed to pesticides.
Based on our original hypothesis, the data we collected does not support our claim. The relative abundances of elements within beeswax does not vary in a significant amount between the exposed and unexposed samples, as the differences between peaks are not substantial.
If we were to conduct this experiment again, we would conduct it with larger sample sizes and possibly samples from other parts of the world. In addition, we would do further investigation into whether it was 4-bromine phenyline or 3,5-dibrotyrosine that was present in our samples. We could try to determine how and why these samples could have appeared in beeswax.
Based on the samples that we had, using pair distribution functions, we cannot see any differences between the structure of beeswax when unexposed and exposed. Therefore, since the structure was not consistently different, we do not think that trace amounts of pesticides significantly impact the crystalline structure of beeswax.
Regarding the Brockhouse beamline, future research could entail looking more into pair distribution function bond length, the variation of crystalline structure between a live and dead beeswax, and the patterns found in the medium or long ranges of PDF, an important topic as we did not expect a repeating pattern to appear in our PDF.
For the past year, the COVID-19 pandemic has forced us to postpone in-person meetings, visits, and processing of our samples, as well as traveling to the Canadian light source was canceled. Despite these challenges, we continue to do work on our research. All of our internal and c.l.s. team meetings, as well as Beam Time, have been hosted over virtual video platforms. We had to navigate various video platforms and set up technology, and of course, deal with technical difficulties. Also, this was the first time both cohorts had been in the same room since March, which was another challenge. We had to adapt to the pandemic, like many others, but ultimately understood that science must go on. This connects to how this has affected our view of science, which we will discuss next.
This experiment shows the importance of collaboration. As a group, we all worked independently and cooperatively to conduct our research and all the preparation work involved. Without having worked together so skillfully, we would not have accomplished all that we had. The importance of collaboration was also evident when we were collecting our samples. Thanks to Mr. Muse's efforts reaching out to Dr. Foster, we were able to obtain samples in a much more easy way, once again showing us the importance of collaboration. We hope that we will be able to collaborate following this presentation, as we believe that both of our findings may support each other's research. This experiment also shows the importance of experiments and research studies to help address and identify environmental issues. Conducting this experimentation on whether or not pesticides would affect the structure of beeswax not only showed us how professional research was done, but the impact of said research. In our specific case, conducting experiments on beeswax was able to tell us that while pesticides affect the organisms, which are the bees, they do not actually affect the structure of the beeswax or the abundance of elements. By conducting this experimentation, while it was not supported by the evidence, we now see how this type of experiment potentially helps the environment by both identifying the problem and the negative effects of a substance and bringing this information to the general public to help make a greater change.
We'd like to thank from the C.L.S. Anna Maria Buckler, Dr. Graham King, David Muir for his help with our ideas beam time and analyzing our samples, Amanda Pfeiffer, and Tracy Walker. We would also like to extend a special thank you to the NSERC Promo Science for funding the educational outreach programs at Canadian Light Source and giving us the opportunity to participate in students on the Beamlines program. From UBC, we'd like to thank Dr. Leonard Foster. We would also like to thank him for helping to explain beeswax, bee biology, and causes of bee mortality. And we would also like to thank the STMC Parents Association for funding, and especially Mr. Muse for all the time and effort he put into coordinating and running this program.
Thank you for listening to our presentation. Are there any questions?
This is Leonard Foster. I have a question, if I could.
Go ahead.
Trying to turn my camera on, but it's not working. Anyway, great presentation, you guys, and very well done. I love the ending message that science must go on in the face of COVID. That was great. My question was, do you know what the sensitivity of the methods you used would be? So you mentioned that there are trace amounts of pesticides in the honey, in the wax. And it might be down into the even parts per billion range. Would the methods be able to detect changes at that low of a level?
I'm not entirely sure the exact number for the accuracy, but I know when Dr. David Muir was explaining it to us, we were running our nickel calibrant, which was on the slide. And I believe that showed up just from rubbing our sample on the nickel, and that's how we got the results. So I believe it is quite sensitive and can detect very small trace amounts.
And for the XRF data, I believe that IDEAS can detect the total amount of certain elements within the sample. I don't know in what unit it would be. And what we did was we normalized our data and then put that all in our graphs because otherwise we might have giant discrepancies between our data. So we don't know that for sure at this time, but we think that IDEAS at least might be able to tell us a total amount of certain elements in their sample.
Are there any other questions?
Hi, this is Renee Merzlak. I have a question. So given that you didn't find any discrepancies between the two, can we feel a bit more confident that our honey is okay?
We did not test honey, we tested beeswax only, so we cannot give you a for sure answer at this time. If pesticides have not leached into the wax and shown up in our experiments, it's possible that they also haven't shown up in honey, but we would have to do further experiments to confirm an answer to your question.
Anyone else? Tracy?
I have a question, yeah. So my question, well, first of all, I'd like to congratulate you on a spectacular presentation. That was very, very well done. I'm very impressed. You've had a couple of questions about your science in specific. My question is not about your science, although I commend you on that, because when people start with those questions, it means that they've gotten past the fact that you're high school students and are looking at you simply as researchers. So well done. My question is more about your learning. You pointed out that this is, that you were one of the first ones to take a look at things on Brockhouse and about, you used 2 different beamlines. You guys crammed a lot of information into a short presentation, and you did that very, very well. My question for you is, what of all of your experiences, the beamlines, the COVID, the collaboration, the bees, all of those calculations, what stands out to you that you would be able to use in your future?
Okay, well, I would say that definitely being able to quickly adapt and learn fast is very, very important. That's something I can bring into the rest of my life. For example, with the GSAS2, it was very difficult to navigate that program, and the 4 of us working together to help each other learn it was really beneficial.
And just adding on to that, having a proficiency with computers and knowing how to analyze data and make graphs is also something that we got to practice, and that would be very useful if any of us go into research science.
Yes, to add on to that as well, more generally, I've realized how important data analysis is for research, because you can't even begin to discuss results before you're able to analyze data. And that involves using different programs and adapting to that. And I think those skills with those programs and the data analysis will help in any research or future science endeavors.
As for me, throughout our entire journey, I was shown step by step the beauty of research and experimental science, from having that initial inkling of idea to collecting samples and preparing samples with the help of the c.l.s. staff, including Graham and Amanda, and then to actually collecting our data and analyzing that with software such as the GSAS2 that we've used, and finally to now when we're communicating our scientific results and findings. Just this entire process and how intricate this whole entire journey was really amazed me, and I think I've grown so much along the way, and this project definitely, it was so fun and intriguing. So it further convinces me to go into research science as my future career path.
At every phase in the process of building this experiment, it required a lot of time and care. We had to put a lot of time and care into each phase. And we had to make sure that we, covered all our bases, made sure that we were looking at things from every angle possible. And the patience that I think all of us learned throughout this process will serve us in all of our future jobs and future activities later in life.
A few things that I would take away from this entire research project would be communication, organization, and adapting. But out of all those three, I would take adapting as the biggest one for me. This project, doing a lot of extensive research, a lot of data collecting, it was entirely new for me, right? And I would say that I've learned quite a lot from this experience as a whole. I will tell you though, at sometimes when I was just looking at numbers, my brain was completely fried. So yeah, there's a lot of things I had to work through, especially with COVID pandemic, not being able to see your peers all the time. Communication was an essential need and teamwork. So yeah.
For me, something I took away from this was actually the points of an hypothesis, because even though ours was not supported, I now see how that opens up future research questions, and that's something I found really interesting.
Yes, thank you for that question.
Thank you for those answers. I would like also to extend that question to Mr. Muse, if I could.
What was your actual phrasing of your question, Tracy? I forgot.
As the teacher that was facilitating this group, what's your takeaway?
I was super impressed with student resiliency because it would have been easy back in March when the pandemic hit and we were just like in the really starting of our planning to really just shut it down and say, okay, we're just not going to bother. But instead, you guys were willing to jump on a Google Meet and have conversations, even though we couldn't be in the building together. Dr. Foster spent like an hour and a half one day chatting with us about bees and about research, and then it was eventually willing to help us get samples. And these guys adapted. And it was cool that it was still able to happen despite all the challenges that exist in the current circumstance.
Okay, and you personally, are you taking anything away from this?
Again, it's reinforcing the value of experiential learning for me and finding cool ways to get students really doing science that's not what normal classroom science looks like. Trying to find ways to adapt my classroom science to incorporate some of these ideas. There's challenges like this is a small number of students and it works out well, but scaling it up to a class that you see once an hour, once 3 times a week is more challenging. But try to find some of the themes and ideas and bring them over.
Thank you for that. I hope you're okay with me putting the pressure on you as well as your students.
I am used to it because this is the third time you've done that to me.
Thank you, everybody. That was lovely.
Anyone else have any questions? Does anyone else have any questions? No?
I have another question. Is it possible that maybe the hives from the contaminated and uncontaminated maybe they were close enough together that maybe the bees were, I don't know, like maybe it's just that they're too close together. That's why you didn't see any differences?
Yeah, so as seen on the map, they were actually a bit farther apart than like right next door to each other. However, even then, like bees could fly from one crop to another. Yeah, so that's why it's not as much like an experiment, since we're not like exposing beeswax to pesticides and see what happens, more just research to see the effects of the pesticides in real life.
And it's also worth mentioning that we had a relatively small sample size. So the potential for variation between samples, even when we were controlling for as many variables as we could, was still fairly high.
Plus, I think it was mentioned somewhere in the presentation, but one of our samples, sample D, was a fair bit different than our other samples. So with our small sample size, we can't really say that 11 out of 12 beeswax samples everywhere will have that same structure. So we'd need a much larger sample size to really say anything conclusively.
Thank you for your question. Does anyone else have any other questions? helps. Okay, awesome.
Good job, you guys.
That's nice. We actually get to hear clapping as opposed to all our virtual muted clapping. So I guess with that, thank you everybody for coming to the seminar today. I'm going to stop the recording and we'll continue on with the students. But for those of you attending, thank you again and enjoy the rest of your day.
Bye, everyone.